take a seat so we can start on time. So I'm very pleased to welcome you to this colloquium. We have a speaker who I guess you probably, most of you or all of you know him. Karl Jakobs is a professor at the University of Freiburg. He's also a member of the Atlas collaboration. And in fact, he is?
Still is.
He still is, as I said. And in fact, so he still looks very young. So I can say that he's also a member since the very beginning in 1992, the letter of intent, and even before. And Karl is at the origin of the name Atlas, so we're very grateful for him for this. And his group, he and his group in Freiburg contributed strongly to the discovery and characterization of the Higgs boson and also for new physics searches. They also contributed to the construction of the Atlas semiconductor tracker, and now they're very much involved in the upgrade, so the new construction of the silicon strip detector for the Atlas inner tracker. Karl received his diploma at the University of Bonn and then moved to the University of Heidelberg. There he was a member of the UA2 collaboration, and in fact he was doing QCD studies with the W boson production, and we were able now to see again his measurement. He did an alpha S measurement at the time, 0.13 plus or minus 0.04, an excellent agreement with the current world average at the W mass at the time. And he presented this in 1988 at Morion, the 23rd meeting of the Rencontre de Morion. So Karl, after this, then he moved to Aleph at LEP, and where he did BS oscillation studies and searches for new physics. He was also a member of the D0 experiment at the Tevatron, looking for the Higgs boson and also for new physics. Karl is a leader in global particle physics. He has been a member of a countless number of important committees throughout the world. He was also, in particular, a member of the Scientific Policy Committee at CERN. In 2015, he received the Stern-Gerlach Medal from the German Physical Society. This is the highest distinction for experimental physics in Germany. Between 2021 and 2023, he was chairperson of the European Committee for Future Accelerators, ECFA, and then we are very happy that in 2024 he accepted the appointment to be the scientific secretary of the update of the European Strategy for Particle Physics. And this is precisely why we have invited him today to tell us about the important outcome for our field. So please welcome Karl Jakobs. Thank you.
Yeah, thank you very much, Andreas, for this kind introduction. I think you have read too much about me. It was long. So I'm very happy to be here today and discuss with you the outcome of the European Strategy for Particle Physics process. The title keeps as well the word towards the next flagship collider at CERN. That's where I will put the focus. As you will see in a moment, the strategy covers broader topics, but being at CERN, I think we should focus on the flagship collider. And I'm giving this talk on behalf of the European Strategy Group, because there was a full group behind this in the discussions. So let me briefly recall what is the European Strategy for Particle Physics. It is a cornerstone of Europe's decision-making process for the long-term future of the field. We all know that this is important. It is mandated by the CERN Council. The strategy is formed through a broad consultation of particle physics communities in the CERN member and associate member states and beyond, and you will see this as well during my talk. In the strategy process, recommendations are developed, which will be submitted to the CERN Council for an update of the strategy. CERN Council will do the official update of the strategy. And the last sentence here, this is important. The European Strategy for Particle Physics is not a project approval. If we recommend a certain flagship, it still has to be endorsed and approved and financed, and this goes via Council. Here is the history of the strategy. It started all in 2006. This was the first strategy process, where already it was discussed whether there should be a high luminosity upgrade of the LHC. And then you see here we are in the third update, and the clear recommendation of this, or the mission for this update of the strategy now was to define the next large-scale accelerator project at CERN to reach consensus on the preferred option and on possible alternatives. So this was very clearly expressed in the mission statement, which we got from the CERN Council. The CERN Council has called this process in 2024. There are some motivations which, for example, take into account the progress in the field, the accomplishments, for example, as well on the feasibility study of the FCC and so on. And the aim was to develop a visionary and concrete plan that greatly advances human knowledge in fundamental physics through the realization of the next flagship project at CERN, clearly defined to come after the high luminosity LHC phase. There was the additional sentence that the strategy update should include the preferred option for the next collider at CERN and prioritized alternative options to be pursued if the chosen preferred plan turns out not to be feasible or competitive. In addition, the strategy update should also indicate areas of priority for exploration complementary to colliders and for other experiments to be considered at CERN and at other laboratories in Europe, as well as for participation in projects outside Europe. Of course, we have addressed this as well, but as I mentioned, today the focus is on the next flagship collider at CERN. So this gives you an overview on how the European Strategy Group looks like. As you can see here, there are, for every member state of CERN, 25 member states, we have one delegate. The Director General and the Director General designate were involved. Major European national laboratories were involved. And then there are, in addition to us from the Strategy Secretariat, ESG invitees like the President of Council, working group conveners, and then associate member state representative observer states and other organizations. So it's a big group, as you see here. So let me just remind you on the timeline of the process. It started essentially in March 25 with the first engagement of the community. This was defined as a timeline where the community could submit input into the strategy process. And again, we had a second line at the end of May before an open symposium. And we cannot complain, we got a lot of input. In total, we got 266 submissions covering the flagship, but also many other areas of physics. And then we had, in June, the big symposium, where I assume that many of you were in Venice. In total, we had a participation of more than 600 people, and I think we had very good presentations and also a lot of room for discussions. We did deliberately set it up in such a way that everybody could express his or her opinion. Let me go back to the timeline. So then there was a physics working group who wrote a so-called physics briefing book, and I will comment on the major physics findings. Andreas told me to put some effort on the physics in this colloquium. So to compare the physics in different areas between the different colliders. And then we had a third timeline for input from the community before we went into a closed meeting for 1 week in Switzerland on a mountain called Monte Verita. And there after a couple of days, we came out with the recommendations, which were then shared. And now it is basically handed over to Council, because I mentioned before, we draft the recommendations, and it's now up to Council to update the strategy officially. So, what are the large proposed flagship projects which we discussed and considered in the strategy discussions?
Geef allemaal met ex-collega's en over die future solutions werkt, is ook al gestuurd.
Let me just remind you on the strategy outcome of 2020, the previous one. Already there, it was clearly stated that the highest priority should be an E+, E- precision machine to work as a Higgs factory, followed by a proton-proton collider to work at the highest achievable energy, around 100 TeV. And this was also shared in other regions of the world, for example, in P5 in the US, in the SNOMAS process, and also in Japan and in China. So it's not a surprise that there are 3 proposals for E+, E- colliders, or even 4. Namely, the FCC at CERN as an E+E- circular collider with a circumference of 91 kilometers, covering the energy range from 91 to 365 GeV. In addition, there are two proposals for linear colliders at CERN, the so-called linear collider facility, which would cover in a first phase the energy range between 91 and 240 GeV. Then it could be extended in terms of RF in the same tunnel up to 550 GeV. The length of this tunnel would be 33 kilometers. And then there's the compact linear collider proposal from CERN, which would, in the first stage, run at 380 GeV and then could reach 1.5 TeV. In addition, there were proposals for so-called intermediate projects, intermediate in the sense that you would use the existing infrastructure of the LEP LHC ring, and you would refill this again in the LEP3 proposal with electrons and positrons to make circular collider, which would go up to 230 GeV. This is the highest reasonable energy given the small radius of the ring, because on top of this, you would have too much losses in terms of synchrotron radiation. Another proposal is to add to the LHC ring a small 9-kilometer circumference electron ring built as an energy recovery LINAC, which would allow to have electron-proton collisions in one of the interaction regions of the LHC. You would collide 50 GeV electrons with the circulating protons in the collider. So these proposals clearly stress that they are intermediate projects in terms of that they would leave room in terms of time, budget, resources for further developments of the machine that can probe directly the energy frontier at the 10 TeV parton scale. So this is the situation. Circular and linear machines. Let me just recap very briefly what are the pros and cons of these machines. I did not put in all the details of the machines in this talk. If you are interested, there are slides in the backup where you can look up the different parameters of the different machines I just discussed. So the fundamental difference is in a circular E+E- collider, you can achieve a high luminosity and power efficiencies at low luminosities. If you look at this plot, this is the luminosity as function of the center of mass energy. Here at the Z resonance, for example, at 90 GeV, you can achieve huge luminosities at a scale of 10 to the 36, 100 times 10 to the 34 per square centimeter per second, and then you lose because of synchrotron radiation. In linear colliders, it's the opposite. You start with low luminosities at low energies, and then you gain the higher the energy is. An additional advantage of circular colliders is that you can recirculate the beam all the time. You can define multiple interaction regions, and it's very clean in terms of Beamstrahlung. To give you some feeling about the ratios of the luminosity compared to the LEP collider, I put up this small table here at the bottom. So at LEP, you had something like 4 times 10 to the 6 Z0s produced, and you come to a scale of 10 to the 12 at the FCC collider, FCC-ee. What is the advantage of the linear collider? Well, it's very clear. The energies can be higher because you don't have the synchrotron radiation, going to 550 or 1.5 TeV, and the tunnel is a straight line shorter at the scale of 33 kilometer. In this 33 kilometer, you could fit all these scenarios which are listed here. You can achieve high luminosity and power efficiency at high energies. In addition, you have the advantage of having longitudinal beam polarization, and you could have upgrade scenarios possible. Even you could extend the tunnel, or you could replace the acceleration technology by higher gradients. So that's stage one. That's the first machine which comes in operation after the high luminosity LHC, mid-40s, 48. And then you can ask the question, what next? Because physics tells us that we should combine precision, which you get with E+E- machines, with high energy for exploration of the 10 TeV energy scale. And this is also shared across the continents. Similar statements were made in the US in P5. So what are the alternatives? If you start with an FCC machine at CERN, then you have an obvious path to go to high energies by refilling the ring with protons instead of electrons, and you could achieve energies in the range between 85 and 120 TeV. The number depends exactly on how capable you are to design high field magnets. If you start with a linear machine, then the obvious path is to stay linear and use more advanced acceleration techniques, like, for example, a click collider or the so-called cold copper, CQ, where you have can achieve higher gradients, or in the ultimate case, go to use plasma acceleration to achieve higher energies. However, there you have to ask the question, can 10 TeV energies be reached on what timescale, and what would be the power consumption, and so on. So these are the scenarios. In addition, there is the scenario for having a muon collider operating at 10 TeV, but as I will show, there are some fundamental problems still to be solved. This is a collider which you would not be able to build in the first stage, but probably up as a second stage machine it can be considered. The dashed lines here indicate that R&D is needed for all of these different machines for the future. So, how did we come to a decision on our recommendations regarding the flagship? There are three important elements. The first one is the physics potential, which I will discuss in some detail. I mentioned already the physics briefing book was released on 30th of September 25. We had 6 working groups on physics, and we had 3 on technology, accelerators, detectors, and computing. The second important thing is that we try to do a project assessment, looking at the proposals and look at the technical feasibility, the required R&D, the risk, the timeline, and so on. And there was a working group report as well shared with the community by the end of October. And finally, as I mentioned, we had the final step for input from the national HEP communities on 14th of November before we went into the closed session. So I will go through the arguments in reverse order, which means I will start with the national input, come to the project assessment, and then discuss the physics. So you may remember that you had discussions in your country, and there were ECFA questions sent by ECFA. And on 14th of November, we sent exactly 2 important questions out. What is the preferred large-scale post-LHC accelerator at CERN? And this is the feedback which we received. You see here the distribution. MS stands for CERN member states in blue. What you see is there is an overwhelming support, namely 24 out of 25 CERN member states, HEP communities, express their favor for an FCC-ee program. This is as well supported by associate members, as you see in orange here, and non-member states in green. And if you want to have the breakdown, you see it in these tables. This is a question which we did not ask, but we got answers. Namely, 20 out of the 24 CERN member states who expressed their preference for an FCC-ee also wrote that they would favor to have an integrated FCC-ee program, namely followed at a later stage by an FCC-hh. And again, you can see the details in this table. The second question which we asked, and where we did not get such a clear picture, is the question, what is the preferred alternative if the preferred option would not be feasible? You remember, this was one of the questions which were in our charge. And as you see from the distribution, there is no consensus. You can identify 3 main axes, namely the one in blue, the first bar up there. Communities said that we should stick to the FCC, whatever happens, stretch it in time if it is not feasible, or descope it, make it feasible. There is another line, the green one, which has got 7 votes in favor of a linear collider instead. And the third bar here in yellow with 5 votes is to have an intermediate program, either the Lab 3 or the LHEC in the lab tunnel, and bridge this towards the FCC-hh. We also asked the question, what is the preferred alternative if the preferred option would not be competitive? This is in the light if, for example, in another country, China, CEPC, would be built earlier. Then you could operate an FCC-ee at CERN. And here as well, there's no consensus, but what you can identify is there are two strong expressions to stick to an FCC, to stick to an FCC-ee, or to the integrated program. Another fraction is here, go directly, in this case, to an FCC-hh. So this was the one important input from the national physics communities. The next one is the evaluation of the projects. How feasible are they? What R&D is needed? And for this, we had an expert panel set up. One of the conveners is in the audience here, Gianluigi Arduini. The second one was Phil Burrows from the UK. In addition to the ESG members, which are listed here, the persons underlined in red here are external experts which were consulted. They were part of this panel. And they came up and ranked the colliders in a very simple way. You have the projects here. And then here you have the technical readiness level, the R&D needed, test facilities, performance, the site preparation, and so on. And they used the traffic light system. So green obviously is good, and red is not so good. Okay, so let me focus on what are the problems in the red area. First, I would like to mention, you see that the FCC-ee here, the second line, got green all over the place because it's a very well-developed program given the feasibility study. But also you have no issues, for example, with a linear collider, LCF 250 or 550 GeV. You have as well green and yellow, and since we have some time, it's expected that the yellow may turn into green as well. So then you have the red areas. Let me comment on them. First, the muon collider. Here, the feeling of the panel is that the technologies underpinning the muon collider design are in the early phases of exploration. A comprehensive R&D program needs to be defined and a demonstrator needs to be built. On the FCC-hh, you have as well some red boxes, as you see up there. One is related that clearly further R&D and industrialization of high-field magnets is needed, both on the more conventional niobium-3 tin material, but as well as on high-field magnets and high-temperature magnets. And then there's the second box, which is linked to the cost of the high-field magnets, further development of this, and hopefully improvements can be made together with industry such that the costs can be brought down. Regarding Lab 3, this proposal, I think, was started to be developed late. There is still an absence of a detailed lattice design and full-scale simulation, which lead to some uncertainties on the projected luminosity. And then, in addition, they have proposed nested quadrupole sextupole magnets in high-temperature superconductors, which, of course, presents as well a technical, low technical readiness level. On the LHEC, they try to achieve high power and high energy for the electrons, and the performance, therefore, depends critically on a very high current energy recovery LINAC. And this leads to uncertainties on the luminosities, which are as large as an order of magnitude. And in order to get more insurance here, a successful demonstration of the so-called Pearl program, which is currently being set up at IJC Lab in France, is vital. So much about the evaluation on the feasibility of the projects. And let me now come to the physics, the differences between the different colliders. It's very clear that beyond the technical readiness, the physics potential and the long-term prospects of reaching the 10++ TeV energy scale are the driving arguments for the choice of the next collider. And it's very clear that precision is needed together with energy. So, obviously, let me start with the Higgs boson physics, given that these are Higgs factories. So let me take some time to go through this messy plot. The first message, which is important, is that E+ E- machines can make model-independent measurements of the Higgs boson couplings. This is a big difference to the LHC. In addition, you can reach sub% precision in several channels, and this represents a significant improvement with respect to the high luminosity LHC. So let me go through these colors. What is shown here is the coupling measurements parameterized in terms of these kappa modifiers. Many of you will be familiar with this. They are introduced to look for deviations of the standard model. If these parameters are different from 1, you have deviations from the standard model. And the measure of the precision is shown here. So this is giving you the precision on these kappa measurements for different decay modes, to Z bosons, to W bosons, to charm quarks, B quarks, and so on. On the left-hand side of these boxes here, you have the benchmark, so to say. In gray, what is the achievement expected after the high luminosity LHC by around 2041. The hadron machines are on this side. The second one in black is the LHEC collider. And then this would be the FCC-ee collider in case you would go directly without any plus or minus machine to the hadron collider. And then you have the electron colliders here, the linear collider facility with the different energy steps, the click collider with the different energy steps, LEP3, only one energy, and then the FCC-ee with different energies up to 365, and then you would combine it with HH, and then the muon collider. So, clearly seen, there is a big jump, for example, in the Z coupling, but also on the charm and on the B quark and so on. In addition, you could measure very well the Higgs boson widths at the E plus E minus collider. Concerning invisible Higgs boson widths, it's also very well done, but here the best precision is reached eventually at the FCC-HH. So keep this color code in mind, because this will be used consistently through the Higgs discussions. If you look at it more carefully, you will see that at 240 GeV, if you would stick only at this energy, the performance of the different D plus E minus collider seems to be comparable. Given the large statistics, the FCC-ee has always the highest precision. If you extend the linear colliders to go up to 550 GeV, then the situation is different, because the TTH, ZHH production, and also the vector boson fusion production become accessible, and you have significant improvements, for example, in KW and K-top, which is illustrated here. So this is the linear collider performance if you stay at 240, and the dark bar is if you would go to 550. So the next message is for rare processes like Higgs to mu mu or Z gamma, the LHC, high luminosity LHC would prevail, and there you would make a significant further step at the end if you would go to FCC-HH. So the next benchmark is the Higgs boson self-coupling. Many of you know this from the LHC. In order to measure this, you would like to see the di-Higgs production, as is done at the LHC. This is the relevant diagram. Of course, obviously, you have as well background and destructive interference. But it's amazing that the present estimates for the high luminosity LHC give you an estimate of a precision that could be reached by 2041 of plus minus 27%. Obviously, in order to measure the Higgs self-coupling, you need di-Higgs production, which you do not get at low energy E plus E minus machines, running at 240 or 360 GeV. In this case, you would have to determine it from the single Higgs boson production, which has sensitivity through loop effects. For example, this loop here, there you would have a triple Higgs coupling here. It turns out, and in order to extract a significant measurement, you need two E plus E minus energies in order to break degeneracies. And in addition, you need to constrain other contributions in the loop. This is why this indirect method is less powerful. So at the FCC-ee, you would have to use an indirect method, which combined with high luminosity LHC would bring the kappa parameter down to a precision of 17 to 20%. You improve this at the level of plus minus 10% at the LCF 550. The ultimate precision you would reach at a hadron collider or at a muon collider, bringing this down to something like 3 to 4%. Let me move to electroweak physics, electroweak precision observables. This is another very important physics area. Here it's obvious that you have an impressive precision in circular colliders due to the large Z sample. Let me recall again, you are at the scale of 10 to the 12 for both FCC-ee and LAP3. So this is reflected in this table here, where you see the uncertainties for the Z boson measurements, R ratios at the plus and minus colliders, but also you can look at the W boson mass. And you see here we had to change the scale. Instead of our used MEV, we go to KEV. This is the current value, current uncertainty, and at the FCC you would reach a statistical uncertainty of something like 4 keV for the Z boson mass. The bracket of 100 is giving you the experimental systematic. At the LCF, it's estimated to be at the scale of about 200. LAP3, again, you see here the difference. Given the large luminosity, LAP3 would outperform here linear colliders as well on the electroweak sector. Let me stress that reaching these uncertainties places strong requirements as well on the detector design in order to bring the systematics down. As I mentioned, it's unprecedented precision for the electroweak precision observables at the FCC-ee, which is also very nicely shown here in this benchmark plot, which is sometimes considered to be the ultimate plot for the test of the standard model, the direct measurement of the top mass against the W boson mass, comparing the direct measurements with the predictions from the standard model. And you see here, looking at these ellipses, what you expect to get at the FCC-ee from the Z program. Theory uncertainties could as well be a limiting factor in realizing the full potential of the statistical power, and that's why significant and sustained investment in theory work is needed as well. Another way to look at it are these so-called oblique parameters, S and T, which define sensitivity to BSM models. Again, here, if you look at these different reaches in terms of these parameters, standard model is at 0, 0. Deviations from the standard model would give different values. Look at the size of the ellipses. It's clear the highest sensitivity lies in FCC-ee and LAP3. The effective couplings to fermions is an example where the statistical power cannot always be used, because here linear colliders would clearly profit from their polarization effects. Looking at left and right-handed couplings for fermions, you see here the ratio between linear colliders and FCC is less pronounced as you see it, for example, in electroweak mass and coupling measurements. So, again, still the highest sensitivity would be provided by FCC-ee by an integrated program. High-energy linear colliders would compensate this, as I mentioned, by polarization, and as well at higher energy, they would profit from a stronger diboson measurement program. Going to the top physics area. Here, it's clear linear colliders at higher energies significantly improve the sensitivity to EFT operators in the top physics area. 500 GeV opens the sensitivity to energy-dependent operators. They have strong bounds in the effective field theory fits, for example, on these 4 fermion interactions. You see this down here, which shows the sensitivity to these 4 fermion interaction for different operators. I don't want to discuss details. In this case, the higher this tower, the better it is. So you see here that linear colliders at high energy are higher than the FCC-ee, given their power in the energy. Hadron colliders, in the end, they would be complementary because they probe the QQ bar, TT bar, 4 fermion couplings, and they would provide as well the best measurement for the top Yukawa coupling. This combined is another argument, again, why you would like to pair up a plus or minus collider with a hadron collider at a later stage. Another way which shows the power of high-energy linear colliders is this plot, the sensitivity to effective field theory operators looking for flavor-changing neutral currents in top quark sector. There are areas where the FCC-ee alone would not have sensitivity. Again, this could be rescued by an FCC-HH. Flavor physics. So here the situation is, if you look at the number of B hadrons, B mesons produced, then the real factory is the LHC, or later an FCC-HH. If you look at the number of B mesons and B baryons, you have the different flavors here, produced by LHCb, 300 inverse femtobarn, which would be reached by 2040. This is enormous. This is the Bell 2 statistics. Labs 3 would have to profit in the flavor physics from the large number of Z decays to heavy quarks, B quarks, C quarks. So the first message is large progress will already be made by LHCb and Bell 2 over the next decade until 2040. You see this very nicely illustrated on the precision of the unitarity triangle. This is the situation as of today, and this would be the situation by 2040. FCC-ee would still improve. However, another important area is for some B decays and also for tau physics, the tera-Z production at future FCC-ee would provide a real step forward beyond what LHCb and Bell 2 can reach. Giga-Z, the statistics which you have at linear colliders, has a strongly reduced potential for B flavor physics. So another example which shows this very clearly is potential in flavor physics, looking for exotic decays. For example, tau decays to mu gamma. These are the limits which are expected to be reached by 2040. The blue diamond is LHCb here. FCC-ee and Labs 3, the green point is FCC-ee, would clearly improve on this, while linear colliders would be far off. The same for tau to 3 muons, or this one, B0 to K star 0 nu bar. Again, you look at this in effective field series, you can as well find complementarity between electroweak programs and flavor programs. Again, these are operators from effective field series, where the flavor sensitivity is shown here in orange and red, and the electroweak sensitivity in green. So you have operators where flavor plays a very important role and goes beyond electroweak. So the message is completion of the high luminosity LHC and Bell 2 programs provide major improvements of the flavor bounds. Further improvements are possible with FCC-ee, and there is nice complementarity of flavor and electroweak bounds. Also, studies shown that you get a perfect coverage, a full coverage, if you combine in effective field series measurements from the Higgs area, electroweak, and flavor. Very briefly on the strong interaction. Of course, one important measurement is the precision on alpha S. How well can you measure alpha S at future colliders? It turns out, you see here the reach for different colliders, a precision at the level of plus minus 0.1%, which is non-trivial, but needed if you want to exploit the high statistical power, can be reached at FCC-ee by the large number of Z decays, but also in deep inelastic scattering by LHEC. In addition, LHEC would deliver significant improvements on the hadron structure. This is shown here in the famous plane of Q square versus X, where LHEC would greatly enhance this red triangle here, extend the kinematic plane by neutral current, charge current measurements in deep inelastic scattering and heavy flavor production. So, BSM physics. The need for future collider program that can fully leverage both precision and energy is needed to cover the widest range of observables at different scales, below, at, and above the weak scale. An example for this is shown here. A new force, a Z prime. You have here the coupling strengths versus the mass of this object going up to 100 TeV. You would have indirect sensitivity in E plus E minus colliders, and this plot clearly shows the higher the energy, the better. So this would call for a highest energy E plus E minus collider. The same sensitivity you would reach with FCC at higher energies. This is again indirect search, but then you would also have up to 40 GeV about direct access of this Z prime in direct Rayleigh production, for example. Another area is the sensitivity to new physics below the electroweak scale. Here, typically feebly interacting particles are required. This requires a strong synergy with dedicated experiments and fixed target experiment to provide maximal coverage. Shown here is an example of a heavy neutral lepton. This is the mass of this heavy neutral lepton, and this is a mixing parameter. In this case, the mixing is done with electron neutrinos. In the briefing book, you find all other plots as well for different mixing scenarios. So the message is, at high energy of this neutral lepton, the FCC-ee or muon collider would be powerful. If you go to an intermediate range, you could profit from the very large decays of Z bosons again, involving the heavy neutral lepton. So the FCC-ee would have a huge sensitivity here. If you go to lower masses, then you would have to look for beam dump experiments, like, for example, the ship experiments, or also using LCF as a beam dump experiment. Some people ask the question from time to time, if you have such a perfect precision machine, is there something left for direct discoveries at a higher energy scale? And the answer is clearly yes. These are nice examples which I show you here. For example, if you take the mass of the Higgs boson of 125 GeV, you can look for the parameter space that is still compatible with this measured Higgs boson mass of 125 GeV as a function of the average stop mass. So it's a stop mass versus mixing, and then you get this so-called octopus area, which is uncovered as of today. Precision machines in E plus E minus would have sensitivity in these yellow areas here. If you would build a muon collider up to 10 TeV, you could cover, of course, additional region up to 5 TeV, given the kinematic limit of a muon collider, and the hadron collider could clearly extend this. Another strong reason for the hadron collider is clearly the sensitivity to supersymmetric particles that are strongly produced, like, for example, stop quarks or squarks or gluinos. Here, sorry, the color code is different. The hadron collider in this case is this purple bar. The legend is down here. So a huge sensitivity up to 14, 15 TeV for masses of the supersymmetric particles. Of course, the detailed reach depends on the mass and also on the SUSY scenario, in particular the mass splitting. So these are strong arguments for reaching out to the 10 TeV scale plus with a hadron collider, of course, in combination with an E plus E minus machine. My last slide on physics is, can you learn something about the interesting question on the electroweak phase transition in the early universe? Yeah, this is, of course, important, because if you want to explain baryogenesis, then theorists claim that they need a first-order phase transition. So the difference is shown here. If you have a standard model with a 125 GeV Higgs, it seems that you have a smooth electroweak phase transition, a smooth crossover from a Higgs vacuum expectation value at 0 to a non-zero value. While if you have a first-order phase transition, it would look different. You would have here a bubble between, and then, of course, a prompt transition from this to this one. In order to get a first-order phase transition, which theory like to have, you need physics beyond the standard model, if the Higgs weighs 125 GeV. And now you can ask the question, are you sensitive at the future colliders to such a scenario? One thing which was studied is to have an extended scalar sector, obviously more Higgses. This would modify the coupling to Higgs bosons. It would also modify the shape of the potential. And what is shown here is a scan over the parameter space of a singlet scalar leading to a first-order phase transition for different mass combinations. But the main message is, in this scenario here, all the blue area would lead to first-order phase transitions. And having these additional scalars, you would change the coupling of the Higgs to fermions, to standard model particles. The change is given here in square, and you would change the coupling parameter of the Higgs boson self-coupling. So you can now approach it from both sides. Having precision on the overall couplings, for example, the best precision would be reached at FCC-ee, would exclude, and you would be sensitive to all these points here. You can also branch it from the x-axis by having high sensitivity for the Higgs self-boson coupling. The main message is, given the different collider scenarios, in particular FCC-ee, the precision obtainable at these colliders would cover the vast set of parameter points, yielding a strong first-order phase transition. So this is very reassuring. Okay, so let me now use the last 10 minutes or so to come to our conclusions, which are based on what I showed you, the national inputs, the feasibility of the colliders, and the physics. And here you see a nice picture of the many people from the ESG that were present in these discussions in Ascona. So, intermediate conclusions. We feel that the FCC-ee would deliver the world's broadest high-energy particle physics program. It has an outstanding discovery potential through the Higgs, electroweak, flavor, and top sectors, as well as advances in QCD. Its technical feasibility is demonstrated via the FCC feasibility study. The scope and cost are well defined, again via the feasibility study, and plausible funding models exist. The FCC-ee would maintain European leadership in high-energy particle physics and advancing technology and providing societal benefits. The FCC-ee would also pave the way towards a hadron collider, reusing the tunnel and much of the infrastructure, providing a direct discovery reach well beyond the 10 TeV parton scale. So, in other words, these are all the criteria which were asked by the CERN Council to define a flagship. It would be a flagship project at CERN, which will keep Europe to play a leading role in the field in the future. What about the other alternatives? LAB3 and LHEC as alternative options. So these are proposed intermediate colliders. They offer an intermediate physics program at significantly lower construction cost. I will show you the numbers. However, it comes with a substantially reduced precision physics program. LAB3, I showed you, given the high luminosity, would keep the strong electroweak and flavor physics program. However, it doesn't have a top program. And on the other hand, it would give improvements to Higgs physics with respect to high luminosity LHC, given the plus E minus machine and precision. LHEC has a strong, very strong by definition QCD program. It significantly extends knowledge of the proton structure. The overall precision program is, however, limited, although some improvements on Higgs physics, for example, Higgs to CC bar, can be made. Overall, both colliders, LAB3 and LHEC, we think would not be competitive with an FCC-ee-like collider, where, for example, a CEPC build, maybe not today, but in 5 or 10 years from now, if CERN would choose to go this way, they would not be competitive. To provide a long-term physics program, they would need to be complemented by an energy frontier machine, such as a hadron collider. Taking everything together, we think that these colliders are not flagship colliders. Linear colliders. So, as you saw, they have a substantially reduced precision physics program, less strong electroweak physics, non-competitive flavor program due to the lower luminosities at lower energies. However, operation at 550 GeV or higher would offer competitive programs in Higgs and top quark physics, even better. However, overall, also these colliders would not be competitive with an FCC-ee-like collider. Both colliders require a new tunnel of about 33 kilometers to reach their ultimate energies. An additional disadvantage is the path towards 10 TeV collisions would require plasma wake field acceleration, which is not yet proven to be viable today. So taking everything together, reduced physics, not competitive with an FCC-ee-like collider, and currently no path to 10 TeV, felt that we should also not rank them as top alternatives. So then we looked into a different scenario, which is a so-called descoped FCC-ee. We were convinced by the FCC-ee, however, we would like to make it financially more feasible. So how can this be done? This goes in the direction of descoping the FCC, that you would remove the top program, that you would construct only 2 rather than 4 interaction regions and experiments, and decrease the RF power from 50 megawatt to 30 megawatt. This measure would reduce the construction cost by approximately 15%. Here are the savings. So this number doesn't seem to be large. And it is not large because a base cost for the FCC is the tunnel, which is at 5.5 billion already. And you cannot squeeze too much out of the machine. And the tunnel we need to dig. Although this would have a significant impact on the breadth of the physics program and the precision achieved, the de-scoped FCC-ee would still provide a very strong physics program and a viable path towards high energies compared to the alternative collider options. So what would be the luminosity? The experts, Michael Benedict and Frank Zimmermann, did a scaling. It would be the luminosity of the FCC-ee multiplied by 3/5, giving the power ratio, multiplied by 2/4, given the experiments, and then you could gain something back by optimization of machine parameters if you have only 2 instead of 4 experiments. So the suppression factor is something like 36% of the original FCC luminosity, which is still sizable, but it brings you in the area of lab 3. These staging scenarios, which are listed here, are nice in the sense that should additional resources become available, it was triggered by the financial feasibility, these de-scoping scenarios would be reversible. You could add more RF power at some stage to go back and have a top program. You could, in principle, you could as well increase the beam power, and in principle, you could as well construct additional interaction regions. So, what is the impact on physics? Just show this on one example here. Again, the Higgs couplings, the kappa parameters. In this case, the color code is identical, but there is one additional bin, namely FCC-ee here. This is in blue, the FCC full performance, and this is if you would go to the de-scoped situation. Okay, so you would lose something, it would bring you more close to lab 3, but still, we think it would give a very good path forward. So all this is summarized in this plot here, the physics potential and the comparison of the different colliders. So what was done here by an ESG working group is try to rank the colliders for their performance in precision physics, Higgs, electroweak, top, flavor, QCD, and in BSM physics for different scenarios, compositeness, SUSY, QCD, electroweak, dark matter, and so on. And what you see here, clearly, the highest performance, the higher the better, is given by the integrated FCC-ee plus HH program. On the electron machines in first stage, the FCC-ee dominates. This would be the ranking. And compared to this, the de-scoped machines would be this one, very close to lab 3, but still better than the linear collider machines at 250 or 380 GeV. If you would go to higher energies, but this will cost money, you could catch up. So, this is an important table, and I will spend some time on this, and then I finish. Shown again here is the different machines. And then the different criteria which are used to come to a final conclusion. So, what is the potential for precision physics? I've just shown you this plot here. If you measure the height of this tower or add up the scores, then you come to the numbers which are given here in this table. So again, the color code is green is very good, highest performance. The highest rank is here for the full-fledged FCC on both precision physics and BSM physics, and you see the ranking of the other colliders compared to this. The next column is physics versus CEPC versus a potential FCC-ee-like collider to be built in the different other regions of the world. The only one which is competitive is obviously, by definition, the FCC-ee, if it comes early enough, if CERN takes a decision early enough. The next one is the technical readiness based on the assessment of the working group 2A, and you see here green colors for the FCC machine, but also for LCF. And yeah, for both variants of LCF. The next column is the cost. So the benchmark is FCC-ee at 15.3 billion Swiss francs. Now, are the other colliders cheaper? By definition, the D-scoped is cheaper. I showed you, we saved the 15%, brings you to 12.9. By the way, this includes the CERN part for the experiments. The LCF, if you would stay at 250 GeV, you would be cheaper. You could build this collider with 9.5 billion. However, you saw that for the physics potential, you would like to go to higher energies. If, however, you go to 550 GeV, you are at the same order of magnitude as for the FCC-ee. The cheaper options are those options here where you reuse the LEP tunnel. For LEP 3, you would be at a scale of 4 billion and 2 billion for LHEC. So the overall conclusion from this table, and I forgot one important column, which is the last one, which is the path to 10 TeV or higher. This is clearly opened if you have the tunnel for FCC-ee, also obviously in a D-scope version. It would be red if you would go for a linear collider, because in this case, you would have to rely on plasma acceleration. It is yellowish if you go to the LEP scenarios, LEP 3 and LHEC, because eventually at some point you would still need to dig a tunnel of 90 kilometers to have the FCC-HH or to build a muon collider. So our conclusion from this is that the FCC-ee stands out as the unique option that offers both a concrete plan, has an outstanding physics program, and a clear vision for the long-term future of the field, paving the way towards the 10++ TeV scale, reusing the tunnel for PP collider. And it would maintain European leadership in particle physics. So then we come to the Ascona recommendations. The recommendations are clear. The next flagship collider project, the electron-positron future circular collider, FCC-ee, is recommended as the preferred option for the next flagship collider at CERN. A D-scoped FCC-ee is the preferred alternative option for the next flagship collider at CERN. At this stage, without knowing the reasons for which the FCC-ee would not be feasible, other alternative options are not ranked. Given this, you can ask the question, what will happen if the FCC-ee will not be feasible? I think given the statements on the previous slide, the message which we would like to give is after this long process, we think that everything should be tried to see if the FCC can be built. If it fails, then we have a crisis. Why can it fail? While the FCC-ee has been demonstrated to be technically feasible, its implementation remains subject to uncertainties related to financial viability and the potential emergence of unforeseen challenges, notably those associated with the tunnel construction. The tunnel is not there yet. In this case, we discussed this as well in Ascona. In this case, we think that a new, probably a lightweight, strategy process should be launched as soon as the result is known in 2028 to define an updated plan. In other words, we would like to discuss about option B or option C if we know that this option A cannot be realized. So, finally, let me share some other general recommendations. I will focus on the first one. There was also a very large consensus in Ascona that the full exploitation of the physics potential of the LHC and the high luminosity LHC and the completion of the high luminosity upgrade remain the highest priority of European particle physics. And every effort must be made to complete the high luminosity upgrade within the current schedule. It's clear if we fail on the high luminosity LHC, it will be hard to get the next collider. And in addition, there is good physics to be done at the high luminosity LHC. And we should all work to make this a success. On the technology, let me just comment very briefly on the accelerator technology. Here, our recommendation is, in order to realize the visionary plan presented, the highest priority must be the development and industrialization of key technologies for the FCC-ee plus HH, which are clearly advanced superconducting and normal conducting RF structures, efficient RF power sources, accelerator quality magnets in the 14 to 20 Tesla range, including those based on high temperature superconductors. We think that this, in particular the last one, is important because it also needs probably cooperation and collaboration with industry. Then high current multi-turn energy recovery could be important step towards power efficient lepton accelerators for a broad range of applications. And on the longer term, we think as well that some investment should be made in development of high gradient wake field acceleration and those underpinning bright muon beams. And obviously at that level, one would as well like to cooperate with international partners like the US initiative on the muon collider R&D. So finally, the ESG recommendations have been shared with you in December. Meanwhile, we have written additional documents, the so-called deliberation documents, which contains more detailed explanation to justify the recommendations along the line what I shared with you. And then there are additional reports from the working groups. These reports have been shared with Council. What are the final steps? The Council deliberations will take place in their session in March 26, and then the official update, hopefully of the European Strategy for Particle Physics, by the CERN Council will be made in a dedicated meeting in Budapest on 21st, 22nd of May. And this, at that time, this will be the official release of all strategy update documents, and CERN is working on accompanying brochures to explain the science case of the preferred project, namely FCC-ee, to decision makers and the public. And the final deliberations on project approval by the CERN Council will take some time because now you need to try, if the strategy is updated, you need to try to realize it. This needs discussion on resources, and this will take 2 to 3 years. So 27, 28 is the benchmark here. And finally, let me conclude with the statements that I think a very clear and strong message has been given by the European Strategy Group, and all efforts by Council and by the CERN management, by the communities, should be made to make FCC a reality. Thank you very much.
Thank you very much, Karl. Thank you very much, Karl, for the very clear and strong messages, including that on the high luminosity LHC. Thank you. So we have, there are in fact almost 300 people on Zoom. But I would like to start since this is a CERN colloquium, start the discussion here, questions, and then there will also be the opportunity, of course, on Zoom to ask questions. So maybe in the room first, who would like to ask a question or make a comment? Vitek.
Can I comment? You see, all these projects are quite beautiful. You see, but you mentioned at the end that there may be a problem with the tunnel, and I would like to mention also that the present timing of this project, however nice is it, is subject to lots of problems, like for example, fragmented world.
Switch on your mic.
Can you hear me?
Can you get closer to the microphone?
Yeah. Okay. So. There are several problems which are specific to our times, like, for example, the rise of the populistic parties, which are not for science, you see, or the question if China or Russia or US would finance, and all kinds of problems that I'm sure that you are aware of. My question is about timing. So, given the state of the art, you see, of the politics that would contribute to financing of this project, to me it is very important to stress something that you didn't consider, or at least I do not know that you consider at this exercise, that we would need a project which would have 3 ingredients which are very important. The project that would start immediately after the LHC, that would use totally the existing infrastructure, and the project that will be large enough to justify the electrical energy and the infrastructure of CERN. And none of the projects that you have discussed, however beautiful they are not of the project of the time. What would happen if, for example, due to political reasons, or for example, tunnel reasons, the high luminosity, high energy frontier cannot be attained immediately. So given that there is none of the project is addressing this, neither, you see, none of the collider, and this is the reason that I'm making my comment, that there is one project which tries to fill this gap in between the end of the LHC, the project that could start immediately after the LHC, continue for 10 or 15 years. It is called Gamma Factory. And its physics potential, if you consider the physics potential not only for particle physics, but integrated physics potential for atomic physics, nuclear physics, applied physics, and astrophysics, it's probably as large as the one of the FCC. So if at any time you would consider in 2028 the project that would be less attractive from the point of view of particle physics community, please consider for the first time Gamma Factory project.
Thank you, Vitek. You wanna?
Yeah, I think, Vitek, I would not be so pessimistic. Of course, it's difficult to get any project of this scale approved, but we always faced these difficulties at the time of the LHC as well. It was a similar discussion. So I think we should try. We should convince the CERN member states and beyond to embark on such a program. I think their physics reasons are very strong. And as you saw, we were not so keen to discuss other alternatives, for example, alternatives reusing present infrastructure, because there's a clear message. We should have a plus or minus precision machine and the high energy frontier. And if the FCC would fail, as I said, then in my personal opinion, we should recall a strategy in 28 or whenever and discuss. And then, of course, other options, depending on why it fails, must come on the table. But today, it's too uncertain and too early.
Thank you, Vitek. Thank you, Karl. Other questions? Daniel.
Karl, 5 or 6 years ago, we had another alternative, which was the high-energy LHC. I suppose it's dropped from the horizon because of the difficulties with developing the thin superconducting dipoles. Have we understood what went wrong with the 4 dipoles, which were 11 or 12 Tesla, we put down in the tunnel 4 years ago, and then we had to retry them because they were losing memory or their training? Has that been understood? Because we still, in a longer term, expect something from niobium tin.
Yeah. So the high energy LHC was not considered in this present strategy round. It was not proposed, and also it was not proposed maybe because the last strategy in 2020 declared that this would not be an attractive option, given that the energy jump would not be large enough. Yeah.
Okay. Thank you.
And the costs are, of course, linked to the magnets. Yeah. But whether the magnet problems are understood, I don't know. Maybe someone else can comment on this.
Okay, yeah, so it's probably for the next after machine. Thank you. Other questions? Also maybe from the early career members here.
Yes, Fabian.
Yes, please. No, please.
Karl, thank you for this very precise message. Now, when you quote precision on the various physics parameters, you of course imply a certain integrated luminosity, hence number of operating years. Should we not include also in a price comparison the corresponding operating costs for the various physics scenarios you have mentioned?
Yeah. So, I mean, you have seen in some of the figures, there was a timeline on. Yeah, for example, all the colliders were compared for 10 years running, 15 years running, and so on. We also looked at the operation cost. Yeah, they also were brought to us from the different projects. Of course, there are differences between the different colliders, but they are not so striking. Yeah, was looked at, but they don't make the decisive argument.
Other questions? Please, Michael.
Yeah, maybe this is a slightly ignorant question. So in this overall physics assessment, you also mentioned that the potential of the D-scoped FCC-ee and the Labs 3 is pretty comparable. And the ignorant question is, I mean, that the price tag of the Labs 3 seems to be like a third or so. So can you be a little bit, well, I'm curious why kind of then the D-scope one is the second option, the preferred option. Sorry if I missed anything in your talk about this.
So if I understood you correct, I mean, it was difficult to understand. Your question goes along the lines why the D-scoped FCC was chosen, because it, in physics comparison, it's probably like Lab 3.
Exactly, but quite a bit cheaper.
Yeah.
It's kind of the
So
undescoping.
I think what this table shows it all. Yeah. So with an FCC, D-scoped FCC, you would have the advantage that you would first get the tunnel now, and you would have the potential for an HH machine later. So this is this green bar here. In addition, you would be sure that CERN would keep the technical readiness as well for future. It would keep the potential to react to any developments of a FCC-ee-like machine somewhere else. You would have the tunnel, you would have a future, which is not the case for the other options. So these two marks here are important. And then I mentioned as well that a D-scoped option, in case money becomes available, you could add the top program and you would boost up the performance again.
So it's a prospect.
Which is not possible with Lab 3, for example.
Okay, Elisa, please.
Okay, three fast information questions and one comment.
A bit closer to the microphone. It's not very. Yes.
Does it work? No?
As close as possible, please.
So, you hear me now? I don't know what to say.
That's great.
That's better?
Yeah.
Okay. So, the first, I don't remember the number of slide. It was before 11. You showed arrows from various possibilities to various other possibilities. And I was wondering, is there an arrow from EE once the tunnel is made to mu mu? It seemed to me you made no arrow in that direction. And that's question number one.
Okay, so I think if you have an EE as an FCC at CERN, FCC-ee at CERN, then the natural path is to go to fill the same ring with a hadron collider, with protons. Yeah? So that's why I did not put in a link between FCC-ee going to a muon collider. Could be done, but it seems to me obvious to go this path.
Okay, but if you have the magnets and the tunnel, you could also go to the mu mu.
You could, in principle, go to the muon collider as well, yes.
Okay.
Yeah. I also did not put an arrow from the LCF to the FCC-HH, because I imagine, and many, not only me, many people imagine, if you start with a linear tunnel, it would be difficult to get, in addition, a 91-kilometer ring.
Okay. Then my question on slide 36. Are these D-scoped things prioritized? Namely, does this order, is there a recommendation of the order of D-scoping if needed? Or is it just written?
I think it's not yet ordered, but I have a clear preference here. If I would have 800 million more, I would construct 4 interaction regions straight away from the beginning.
Okay, to prepare for HH. Okay.
No, not only, because the others are easy to be recovered, easier. Yeah? For the top run, I need to install more RF and more power for the third one.
Okay, and the last technical question is, if the HH is built later, can you cover the ground you miss by doing the descoping, or is this descope, whatever has been descoped is lost forever?
I think you saw it as well. For many, many measurements, first of all, you would keep the full electroweak program. Yeah? The difference is not so large. Of course, you would lose some in luminosity, but the electroweak program you would keep. The flavor program you would keep as well. On the Higgs, you would lose some precision, but there, in many cases, the ultimate precision comes from the combination of EE plus HH. So there you would not lose. You would lose, for example, that you would lose in the top program because the top you would not have. But this you could as well partially recover later with an HH, but not on all operators which I've shown you. For example, the 4 fermion operators where leptons are involved, you need a lepton machine. Yeah? But you cannot have everything in life.
The last thing was about Council. So when you give the timeline, this was before 11.
The timeline of the European.
The timeline.
Yes. This
Okay.
Sorry.
So just to point out, as you said, it goes to Council, but it starts in Council. So I would put the timeline in 2024 when the group was established, and not put the date of submission of main contributions. So I think the logic is Council made the decision to have the European Strategy Group now, that is in 2025, and then go. Yeah, so I think in the timeline you should put it from Council to Council.
Yes, okay, from Council to Council.
Says the previous Council President, yes.
It is in fact on the slide, but it's hidden by this nice graph here which displays the number of submissions.
Thank you very much. So maybe I would like, yes, so you will have your opportunity, but maybe make a quick jump to Zoom in case there are questions on Zoom. If you please raise your hands. There's no hands raised for the moment. There's one, Philip. Philip Bloch. Please, Philip.
Hello, Philip Bloch from CERN. I think and Imperial, most of you know me. I have a question on your slide 39, I think. Yeah, which is probably, yeah, I think it's the time scale, and I mean, this is table 39.
39. 39.
39, yes, okay, yes. Yeah, if I understand well, the date, the time scale, the first date is when it could be ready, right? Okay, to 2046 or whatever. Is that correct?
Yes.
Yeah.
So
I find it, yeah, let me ask my question. I find it very hard to believe that a 15 billion project, which requires the construction of a new tunnel, 100 kilometers or 90, with all the political difficulties and the local population, which he may be against and so on. I think to find that can be ready even earlier, even slightly earlier, than you reusing an existing tunnel and with a project which costs 4 times less. I think this is not natural. I don't understand that.
So I'm just repeating as I understood Philip's question. So the question is, well, how can the FCC-ee be earlier in time than LEP3 while you have all the infrastructure to build for FCC-ee while not so necessary for LEP3?
Okay, so let me comment on both of these points. So the timeline 2046 or 47, 48, I think it's not completely sharp. Depends on, you need to construct the large FCC tunnel. Hopefully CERN takes a decision on whether we go ahead very soon, because you need to construct the tunnel somewhere beginning of the 2030s. So then you need some time as well to accumulate finances in the present model. You need a gap between 2041 and 2046 or so in order to make a plausible funding model. This is one of the main reasons. Why it is longer for LEP3 is because you have to take out the LHC machine, which is a big effort as well.
Okay, thank you. So then maybe there are no more raised hands, so maybe we continue in the room. I think up there, Christian, and then we start here.
Thanks, Karl, for the very nice talk. I especially like the idea of the de-scoping, and then in the end you can add something back in. So I have a bit of a naive question. So you kind of start in the council to have the European strategy. Then now the European strategy is pretty clear. It says, or let's say the survey is pretty clear, except Bulgaria, for some reason, almost everybody says FCC-ee. This was something that I feel like was kind of floating around in the air before we took around the strategy, maybe not that clear, but now we have it in black and white after a nice process. So why does it now take 2 years after we give it to the council before they make a decision? Can you elaborate on this a bit?
Yeah, I think CERN has 25 member states who finance CERN and have to finance and carry this project. And as you see from this table, this project has a big financial volume. Okay? And you need to convince the member states, the ministries in these member states, the decision maker, really to embark on this. I hope that our strategy process gives them the feeling that the community stands fully behind this as a very strong message. And as I said in the very end, I hope that they feel obliged to try to make it work. But finding 15 billion and getting a tunnel of 91 kilometers is non-trivial. And that's why it takes so long. And in some countries, please correct me, the council presidents, if I say something wrong, in some countries, it also needs to pass parliament.
Thank you. I think we had, maybe you first and then Eddie. Okay. Maybe choose the other microphone.
Hi, thanks also from me for the talk. So you said on, I think it was page 46, that we have the high-level recommendations and then the more detailed recommendations have gone to council. Out of curiosity, are these going to be available to read later or at some point, or are these going to be restricted documents?
Well, the recommendations, as it says here, have been released on 12th of December.
Yeah.
You're asking about the deliberation document, right?
Yeah, exactly.
So I think this, we are mandated by council. I think these documents first should go to council and they should decide whether they and when they are released.
Okay, thank you.
If you want to comment, use your mic.
You have your microphone.
Yeah, it's really up to the council, but I can see no reason why they shouldn't become public.
Thank you, Clara. So then, please.
Karl, I was just wondering, if you have 4 FCC-ee detectors, what's the best way to make them different and complementary in design?
This is a question which we did not discuss in the strategy. I think this is left to the particle physics community. Hopefully, if this is going to be approved, there will be different detector proposals. You could, for example, think maybe one specializes on flavor, particle identification, more than others, things like this.
It's an interesting question. It's really not so easy, actually. It's different from the Hadron Collider. Any other questions? On Zoom? I see none on Zoom. Okay, so then we're done. Thank you very much, Karl, again.